No, I haven't looked at the next chapter. Well, I mean, like, I'm not that bad where I cannot do like schoolwork. I just can't do like exercise.
And the one day where I'm able to.
Yeah.
I'm stuck with one.
Gross.
One, just as sick as I am.
What happened?
He's-
Carmen's place?
Oh no, I was at Carmen's place and she made us chicken and rice and really good chicken and Gouda cheese. And then we bought beer and then it just kind of went downhill and then we drank rum. And it was just like, whoa.
Wait, Juan is still as sick as you? Why is he?
He exercises when he's sick. He's really weird.
I don't
No, you're
really
fine.
want to be with him when he's
I don't know if he's still sick.
He looks pretty silly.
Stay to 18th. Stay to 18th.
Yeah, wait, yeah.
Good morning.
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 Here's what I start today, couple things. One is that I know that some of you are beginning to get a little nervous about what's going to happen a week from Friday, which is the day we have our first test. What's going to be on it, what's not. And I've noticed, not just with you, but over the years, that when I ask students, please to read this background material, and please keep up with the lectures, that they don't always do that. And they're usually the ones that are asking questions that are pretty obviously answered if they do that. So I'm suggesting do that. The exam's going to be based on these lectures. I get tired of saying that. Some people say, you really mean what you write? And the answer is usually, in that case, is yes. So if you want to know what's going to be on the exam, be understanding the material of the lectures. And the way to do that is to keep up with them every day, take those notes and review them and translate them or whatever is necessary. Now, the last couple of lectures have been based on formal lectures that I've written out in the class, as today is tomorrow's will be as well. And there's absolutely no reason to write down everything that I say about it. They're going to be printed. Here's the next two lectures right there. And they'll be posted on our website. Today, what I will do, rather than try to just touch on everything that's there, is just talk about a little bit, just highlights, and give you an idea of what the purpose here is. But if you don't download that lecture and study it and read it, then you're going to come up short of the right. First. Let's see. One other thing. On Friday, we talked about some notation, about trouble with these and these and rows and mass density and number density. I've told you before, and probably will again, that we have more things to label than we have letters. So letters have to serve a duty and have different things in different contexts. Today we're going to use a row again, so we're going to use a row of some function times the derivative of that function, and that's going to stand for the probability that whatever the function is, x, is in the range between x and x plus dx. So it's going to stand for probability today in the next few days. So try to keep them straight. And I'll try to keep them straight. Can't promise. I'll try. All right, so what do we do today? We're going to talk about Maxwell's distribution of points and velocity phase space. Now, sometimes, and more often than not, this is called the Maxwell-Boltzmann distribution. And that's fine because they each play a role in it. As I will explain to you, Maxwell deduced by the principles of science that I've been talking about. And by the way, they go reasonably well. You're going to see that game played just absolutely brilliant. Could be an eye-opener. So Maxwell did it, as I said, when you are interpreting observations in science, you have to make a guess. You have to guess. Well, maybe this would work. Maybe this is the model. And Maxwell's guess was proven by Boltzmann to be the only one consistent with the second law of thermodynamics, which we studied very well. So Maxwell guessed that Boltzmann proved couldn't be any other possibility. So that's how this called the same Maxwell-Boltzmann distribution. All right, so let's get underway with this. It takes a couple of days to do this because we not only show you the distribution, but we'll look at some implications of it as well. So let's consider the model gas of n identical molecules. They could be different, simply just going to be n identical molecules. Each of mass m and volume V at equilibrium at temperature T. So that's the same model we've been talking about right along. The probability that any one of those molecules is in some differential volume element in that overall volume. As we talked this before, this is physical space. So here's our coordinate system set up somewhere in or out of it. Volume doesn't matter where it is, it's just our frame of reference. This molecule is a part of the gas, part of our collection. So it's in the box somewhere. And rather than just be at a point, we give it some latitude and say your volume element dx, dy, dz, Cartesian coordinates. Now, the volume of the box is just the integral of dV over the box, and that's the volume of the gas. So we say the probability molecule I is in dV as a volume element space is equal to some function of the volume times the size of that volume element. And the function of that volume, we know what it is because this probability is just equal to dV over V of the gas. Think about what the probability of the molecule is inside my fist, which is a certain volume there. Molecule in the screws in there. Well, it's volume in there divided by the volume of the room. So that's pretty obvious. And the number of molecules velocity equal to the total number of molecules times the probability of that molecule is in that body times dV. So this is the number. That's trivially, volumes should be very obvious.
Oh, can you scoot the paper over to?
Why am I doing it? Got the same wrong. I need to tilt that up.
Thank you.
Is that better?
Yes.
Okay.
Oh wait, that was worse.
I can blow that down a little bit. Try.
Oh, that's as zoomed out as
See
it
if you
goes.
want to do it. Sorry about that.
It's okay.
All right. It's radio on, so. All right. So I just talk about probability molecule in a box somewhere and get this notation down for us to think about. Now, let's talk about velocity space. This is the velocity phase space. Every molecule in the box has some motion at a given instant, and that motion is represented by a point in velocity phase space, which is, I like to say, lit up if that molecule is moving with that velocity. And if it changes velocity, that point disappears and new one appears somewhere in velocity space. So this is an interesting, interesting time space, velocity phase space. Well, again, we've got a volume element. I let it be a Cartesian volume element, dvx, dvy, dvz. There as many points in this space as there are molecules in our box. And if you did the exercise I left to do on Friday, calculate the number of molecules per cubic centimeter there in this room right now, you found it was about what? There's about 10 billion molecules per cubic centimeter. And that's a rather heap. So it's a bunch of molecules we're probably talking about. That's somebody we don't have to count it right now. So, in velocity space, we have the probability any molecule is in dV. Now I've got to put arrow over it. I know that may look like a volume, but it's velocity. Probability that are in that little box up there must be, just like with physical space, some function of velocity times the magnitude of that box. And so we call this function rho of v. And we don't know what it is. Rho of capital V for volume is just 1 over V. We don't know what this is. That's what we're trying to find out. So we have a number of molecules with velocities in the range between V and V plus dV vectors, and is equal to the number of molecules times the probability of the molecule is at the vicinity of dVE times dV. Boy, draw a box on this because you can't wrap your mind around this and sort of keep it in mind today, then nothing else I say is going to make any sense.
Oh,
Wait.
we kind of missed it because it was low.
Say again?
It was too low on the screen. We couldn't see it. All right.
Could we just lower the projector screen?
What do you mean by lower? That,
No,
that,
this,
that.
the screen.
Oh,
Does
that
mean
screen
lower?
right down all the way?
I feel like that
Back.
would probably fix it.
Yeah, small straight. Good idea. Yeah, always remind me to do that, but yeah. Should be all. Is that better?
Yes, much.
Alright, so it's at this stage, we know how to write expressions, we know how to write formally what we mean by the probability of a molecule have a certain velocity or in a small region of velocity space, and we know how to tell how many molecules are in there if we knew that function. We don't know that function yet. So, the question is, how do molecules velocities leave and enter some volume element in velocity space? So we set the stage. We have physical space, we have velocity space. In velocity space now, got a volume element there, Vx, Vy, Vz. And at any moment, there's some points in there, and our postulate was that on average would be some constant distribution. Be little fluctuations, but if you average it over a reasonable time, there'll be a certain number in there. Now, the question is, they're not, even though the number in there on average is fixed, they don't stand for the same molecule, because they represent only a molecule moving at that velocity in the real ones. So how they get turned off and on, that's what I want to know. Does anybody know? Anybody have an idea? What happens in real space that throws a molecule out of that box, out of that space in velocity space? Or throws it into, yes.
Collisions?
Absolutely. That's the only mechanism. The molecule has to change its speed, change its velocity. And the mechanism to do that is colliding. And when that happens, then two molecules change. These are pairwise collisions we're talking about. So every time that happens, two molecules, their points in velocity space sitting here, these molecules are moving through space. And their points are sitting there smiling, right? Everything's happy. All fine in the world. And then all of a sudden, boom, and those points go out, and two more appear somewhere else. Right? So they're thrown into a box by collisions that happen to make one of their velocities appear there, and they're thrown out of that box by collisions that make one of the molecules whose point is in there be thrown out. And it's by collision. So we have to talk about collisions. That is the mechanism. So let's consider one generic collision. And this is just the one that we're going to focus on. It could be any collision, it doesn't matter. But just here's a representation of it. These collisions take place in some plane. Each one of the planes tilt around different collisions, but so I can draw it on paper. And I've got an orange molecule and a blue molecule, which is appropriate for where we are. Molecule number one initially has a vector that looks like it's sort of in the plus x direction. And molecule number two has a vector that's in the minus x direction. So they have a chance to collide, but to collide, they have to be, they can miss each other too. So they have to be aimed at one another enough. We talk about that later, about how we deal with that. But anyway, they make this particular collision. And when that happens, this point, which was over here in velocity space, right here, suddenly winds up out here in velocity space. It was over here now. And this one, whose point was over here in velocity space, side of the line. That make sense? Good. I wish I could. All right. So here is the velocity space, here's the collision. This is a physical space, this is a velocity space. Before the collision occurs, molecule V1, its point's right here. The molecule V2, its point is right here. Okay. And after collision, V1's point is here, V2 point's there. Furthermore, we can say that the numbers of molecules with velocities and velocity points is dV1, and where was that one? That was right here. Is that. You just said the number of molecules was in a certain element velocity space is the number in the box times the probability that one's in that box, which is this row D1, D1. And similarly, the numbers in volume element dV2 for that, numbers in the prime volumes after collision for those. So just rewrite down the counts, these numbers of molecules. Now Maxwell determined the distribution of those points in velocity space by consideration of collision just like that. This is an arbitrary example. In doing so, he invoked this principle of detail balancing that I mentioned and wrote down the postulates of our kinetic blanket theory. The third one was that the distribution of points in velocity space is spherically symmetric. That if you draw a sphere around the origin molecule has zero velocity, a sphere around that, then the density of points near that sphere is uniform around that sphere. If you move to another distance out, it'll change to some other value, but it has spherical symmetry. And then I said this is consistent with the principle of detail balancing, which we haven't talked about yet, we're going to today. And that is how Maxwell was able to generate this beautiful piece of figure we want to see. Real quick. Detail balancing. Maxwell used the principle. Detail balancing. And disprove. So let's think back about this last figure that I had up here about these boxes. How many ways are there for a molecule in real space to have its point thrown, if it's moving so that its point's in here, how many ways are there for its point to be thrown out? And the answer is very easy. An infinitude. The absolute infinitude of points. Not because there's an infinitude of molecules, but because there's an infinitude of ways they can come together. And that changes the direction they rebound. So it's infinite number. That's mind-boggling. How many ways are there for other molecules to collide so that their point jumps into here? An infinite way. Seems pretty daunting if you're going to try to calculate this distribution. So you've got these infinitudes of infinitudes to deal with. This is where Maxwell was really very clever. One of the ways that a molecule can have its point thrown out of that element of velocity space is by this collision that I just showed collision. That's one way. They'll throw the point out of this box. Also throw the one out of this box. We're just talking about one box stuff. That's one way. One way to move a point. EV1 is by the illustrated collision.